Tuesday at 3 p.m. we'll have a help session. Probably be in Beauregard, help session. So if you're able to come, please do. I'll record it as I usually do, and it does count towards extra credit. So if you want to come, it's 3 points for every help session. So if you can't come, just shoot me an email and you can get that credit otherwise. Yeah?
Is there a max bonus?
There is a max. It goes up to 20. Where some of you, if you come to the seminars act to replace, if you miss a help session and don't make it up or whatever, the seminars work to replace those. They're not extra. But some of you, just a few of you are getting close to maxing that out. Did I say the max? 20. Yeah. Okay? Is that clear? And there might be a little bit of an opportunity for a few extra points for the final. Like we'll have an assessment that we'll take, but mostly not. Alright. We went to Johnson Space Center. We spent a few days in Houston. OpenStax. They produce open source textbooks for folks. You guys have been the OpenStax tutor. They produce that and the textbooks. So we went to a conference for that. It was really cool. They have all sorts of textbooks. Hopefully you'll see more and more of those at Nichols because it's good for you. They're good textbooks. They're not just free, but they're good textbooks. Biology has one, calculus has one, A&P, A&P book. So hopefully more and more you'll see that. We went to Johnson Space Center, saw Mission Control. That was really cool. They had all the original stuff when they had them in landings. They even had the ashtrays in the backs of the chairs for the folks. In Mission Control. All right. We have our test on Wednesday. It'll be in this room. I'll send you a message reminding you of that. But our help session's on Tuesday at 3 in some room I'll send you. Our test will be in this room. There will be a seating chart, and I'll have assigned seating. Just so you know, those seats, I have a random number generator. You're not put in your seat for any particular reason. So that's how I assign your seats, just randomly with a random number. Okay, so our test, this is the file that I use to make out the test. These are the topics. So from Chapter 5, we had multi-loop circuits and household circuits and RC circuits. Those are topics that we have left over. So for example, you'll have 3 or maybe 4 questions on multi-loop circuits. You'll have 2 on household circuits. There might be a calculation, like for example, calculating the total current that you have for a household circuit. We've worked some problems like that. And then just basic information about the 3 safety devices we talked about, the GFCI, the grounding, and what was the third? Circuit breakers, right? So make sure you know those, how those work, and just how a household circuit is laid out. It's in parallel and what are the ramifications of that. RC circuits, you need to be able to calculate the charge, current, or voltage at a particular time. You need to be able to calculate the time constant. You need to know when a capacitor is fully charged after 10 time constants. And you also need to be able to identify the charging or discharging graphs for current, voltage, and time. Those are all things that we've done. And you look back at the old test, those are usually the questions that I ask. Those are the questions that I ask, but there are different varieties of this. You want to practice that. And then in Chapter 6, magnets, forces, right-hand rule, and mass spectrometer. There's sort of some crossover in this. So for example, with a mass spectrometer, you might have to use the forces or the right-hand rule, but it'll be in the context of a mass spec. Magnets, what is a magnet? Magnetic domains, north and south poles, no monopoles, that sort of business. The basic, second grade stuff regarding magnets. The forces, how to calculate the force on a wire, how to calculate the force on a charge moving through a magnetic field. Know how to use those formulae and know how to apply them in those scenarios. We've done a bunch of examples of those. Right-hand rule, various applications of right-hand rule like we've done. We have 3 different applications, and we can practice them today if you want. And then the mass spectrometer, that's sort of an application of all those various things. Make sure you know how to do that. That also takes into account that the magnetic force is a centripetal force, and what that does to a particle. It only changes the direction of the velocity. It doesn't actually change the speed of the particle. Let's see, what else we got? Chapter 6, we have light, reflection, refraction, and total internal reflection. Know how to know the basics of light, that historical stuff that we did about is it like a particle or a wave. The people that were involved, Einstein, Newton, Huygens, and Young, know about reflection, the law of reflection. Usually I just have one question. Usually it's one of those where you have two mirrors and you have to figure out what is the second reflected angle. Refraction, you'll have both calculations where you have to calculate the refracted angle using the law of refraction. That's the n1 sine theta 1 equals n2 sine theta 2. And then usually I give you a question or two where you have to rank the speeds of light in different media, or you have to rank the indices of refraction in different media. Where I give you 3 different media and I show you the paths of the light, like we did in class. So make sure that you know how to do that. And then total internal reflection. Remember, that's just a special case of the law of refraction. It's the special case where theta 2 is equal to 90. Don't worry, we'll look at all these things. I just want to give you an overview. And then finally from chapter 7, not much from chapter 7, maybe 3 or 4 questions total from chapter 7. We just did flat mirrors. In flat mirrors, well, let me write down. This doesn't help you very much for chapter 7. I don't usually have this little amount of material from chapter 7 on an exam. But from chapter 7, you need to know flat mirrors, and you need to know that the image distance is equal to the negative of the object distance. You need to know that for flat mirrors that m is equal to 1. That means that the object is always upright and it's the same size as the image. The object and the image are the same size. And then I also want you to know, what do the signs mean for these various quantities. So a negative image distance, that means that you have a virtual image, as you have with flat mirrors. If I have a negative magnification, that means that the image is inverted. If I have a positive magnification, that means that it's upright. If magnification is bigger than 1, that means that the image is bigger. You have a little table in your notes that outlines these. If magnification is less than 1, that means that it's smaller. Actually looking at the absolute value of the magnification, because it can be less than 1, but it can be, say, -2. And that would mean that the object is bigger, the image is bigger than the object, but it's inverted. You follow what I'm saying? That if this value is negative, we just take the absolute value of it. Okay, so know these basic quantities and what these mean for mirrors. That'll be important, and it'll hold the same for lenses and spherical mirrors when we get into those on Friday. Okay? I think that's it. Let's pull that back up. Ray tracing mirrors. Yeah, you might have to do a ray tracing where I give you an object right here and you draw the rays and show me where the image is. You know what I'm talking about? Usually the way I do that, so for example, we did this in class. I draw one ray like that, I draw another ray like that, and then I trace them back to find out where the image is, and the image is there. I could give this as a free response. I could just give one question as a free response, and you just have to draw the rays. Or usually I just give it as a multiple choice, where I'll draw a series of rays, and then you have to pick out the one that's incorrect. So, like for example, in this case, I might draw a ray. Oh gosh, how would I draw it incorrect? I'll probably draw it such that it doesn't follow the law of reflection. So the green one would be incorrect in that case. What you want to look for is that you look for the two rays that cross exactly opposite the object, like this. So you know that these two rays are correct because the image is where you would expect it to be. You won't find examples of that like that in the old test, because usually I don't split chapter 7 up, but you could see that on the test. Emma?
Can you try to write from a star to the left and still have it cross?
Yeah, of course. Yeah, that's a good question. Let's check. So I could draw a ray that looks like this, and then it bounces off, and it's still going to cross where the image is. Where the virtual rays cross is where the image is. That's a good question. Yeah, that's a good question right there. Which of these rays is incorrect? Or I might have you draw them. just try it before you come in. I might have you do it for your response. Okay. What do you want to look at? What's your weakest point? Yeah.
Can you go over some right-hand rule problems?
Sure. There are 3 applications of the right-hand rule. You guys don't forget your multi-loop circuits too. It's been a while since we've done that. We can go back and look at those. I know that magnets are a little fresher in your mind, but don't forget those multi-loop circuits. They're not trivial. They're not trivial. If you know how to do them, they're not that hard. But if you're uncertain about how to do them, they can be difficult. Anyway, hold on 3 applications of the right-hand rule. The first, this F equals QVB. Our fingers go in the direction of V. They fold towards B, or you can think of this as your palm, that B comes out of your palm, and then your thumb gives F. So for example, let's say that I have a velocity vector in this direction, and my magnetic field is in this direction. I want to know the direction of the force. So V is to the right. I don't know how my hands should be oriented right off, but V is to the right, and my fingers need to fold towards the magnetic field. Or I can imagine the magnetic field coming out of my palm like this, and so the force is going to be out of the page. That would be sort of the simplest that you would see. The force here is out of the page. Of course, we can have more complicated ones where you have to sort of work backwards, or ones that, for example, where I have a particle that follows a path like this, where this is my velocity. It starts in this direction, and I ask, what is the magnetic field? Well, in this case, you need to recognize that your velocity vector begins like this, and my force vector is like that. And so my magnetic field that causes this motion is a magnetic field that on this particle causes an upward force. That's what causes this particle to move up. So V is like this. My magnetic force is my thumb, so it points up. And so that means that my magnetic field is into the page on this one. That's one application. The second application is exactly the same, except instead of having particles that are free, I have particles that are bound to a wire. And so, for example, I have a wire, I have a magnetic field that's up. This is my current, although remember it's not really the current that's the vector, it's the length of the wire, but it doesn't matter. And so this is going to be the same as the scenario I did before. The force is going to be out of the page, coming towards you. Could do another one there. Let's say that my current, or no, let's not do it that way. Let's say that I have a current coming out of the page. That's a wire that's coming towards you. Let's say then that my magnetic field is in that direction. First of all, I'll do another example. So I is in this direction, magnetic field is in that direction, so I fold my fingers that way, and so my force is going to be up. My force is up in this case. Let's try it a little bit differently, because you have a question like this, where I don't give you a figure, but I describe them in terms of their axes. And so you'll have to either think about what are those axes or draw a figure yourself. So let's say that my current is in the plus y direction, and my magnetic field is in the minus z direction. Then what is the direction of my force? Okay? You'll see a question like this on the test on Wednesday, where instead of giving you a figure, I give you the actual coordinates. So, probably the best way to do this, well, you can think about it, right? I is up, B is in the negative z, so my force is going to be in which direction? Negative x. Yeah, that's going to be my answer, that my force is in the negative x And it sure better be an orthogonal axis. It has to be plus or minus x, right? It can't be y or z, neither plus nor minus. So f is in the negative x direction. Another way that you could do this is you could draw your coordinate system like this. I is in this direction. B is in the negative z direction. That's going to be like that. And then F is going to be in this direction. I guess you don't need to draw your coordinate system. But you can draw a figure that represents those axes. Just don't be thrown off by that, because we haven't actually done that in class. But you're capable of doing it. You know what those values mean. Okay? All right, the third application is for a wire, and then we actually have some sub-applications for that. So if I have a wire with a current in it, it generates a magnetic field. We calculated that magnetic field. It was mu naught I over 2 pi r. You might have to calculate the magnetic field of one or more wires as well. We can go over that if you want. But that's how you calculate it. If you want to know the direction of the magnetic field, your thumb goes in the direction of the current, and then it wraps around. I always like to use my pen for this. So my thumb goes up like this, and then my fingers wrap around. So on this side, it's going to come out towards you, and on this side, it goes away from you. So into the page, out of the page. You might also see some problems. We've done some like this in class, where you have a wire with some current in it, either up or down, and then I show you a charge that as it approaches that wire, it moves. And you have to figure out what is the current in the wire that caused the charge to move that direction. You remember doing that? You want me to do this right quick? Okay, so a couple of things that you have to recognize. First, make sure that it's a positive particle. If it's negative, then you have to take the opposite of what you found. But we'll say it's positive now. So I have a velocity vector in this direction and a force vector in that direction. So what's my magnetic field? Out of the page, right. It has to be out of the page. My magnetic field is out of the page. That means over here it's out of the page. And because I know what a wire does to the magnetic field, I know on the other side it's opposite what it is over here. So it goes into the page here, out of the page here. So my current that causes the magnetic field, that causes that charged particle to move in the way that it does, is directed upward. The current that causes that is an upward current. Okay? All right. We also have some sub-applications of this, mainly for a solenoid. I guess it really is just for a solenoid. That if I have a current in a solenoid, like this, and I want to know the direction of the magnetic field, when we talk about a solenoid, we're really talking about the magnetic field in the middle of a solenoid. We let our thumb go in the direction of the current, it goes into the page, and so our solenoid has a current that comes out of the page. This is the same application as what we did here. Let our thumb go in the direction of the current, into the page, out of the page, like that. We're just wrapping that thing up in a circle to make a solenoid switch. We calculated that magnetic field. We can calculate it right here. And that magnetic field, what is it? N mu naught I over 2R. Those are on your equation sheet, but you might have to calculate those magnetic fields. Mallory?
How you figure out it goes out of the beach.
Now do that, right? This one right here?
No,
Oh, this one? Yeah. So our current here, when we put our thumb in the direction of the current, it goes tangent to the circle where we imagine it's tangent. And then our fingers go into the page, and then they wrap around, they go out of the page. So if you think about this going up, into the page, out of the page. All right? Marissa?
would be the opposite.
Yeah. So you just change the direction of the current. So in this case, goes into the page, out of the page. So my magnetic field there is going to be into the page. Okay? It can either be in or out. It can't be any other way. That's it for my right-hand rule. Valerie? Yes.
Is that always true? That the magnetic force and the electric force are opposite?
Is usually on those problems it is, and you'll probably see one of those. I haven't finished writing the test, but you often do. So usually in those cases, you have a charge that is undeflected. And those words, when you see them, what that means is that the net force is equal to 0. That is that I have this charge, and I have one force that's up and one force that's down. And so that's why, if it's undeflected, that the electric force is equal to the magnetic force. It's kind of important. I want you guys to understand that often we use electric and magnetic fields to manipulate these charged particles. Does that answer your question? Yeah, I would be prepared for that. How are you? There are lots of examples on the old exams. I would certainly practice those. All right. What else? Go over multi-loop circuits quickly. Yeah. So with multi-loop circuits, you're going to see 3 or maybe 4 questions. You'll see a series of 2 questions where you have to find the correct equation, which we've done a bunch of times, but you'll have to do that again. And then you also have to solve for one of the currents. So let me just give you an example of a multi-loop circuit. So we can say this is 2 volts, 1 ohm, 3 volts, 5 volts, 4 ohms. So when you're looking at a circuit, and you'll also have the currents that will be labeled. So we'll call this I1, I2, and I3. These should look familiar to you. We've looked at these a bunch when we were doing this chapter. You want to be able to write your junction rule and your loop rule. So with the loop rule, remember we had some notations that we used. So if we have a resistor and I'm going in this direction with a current in that direction, if I'm going in the same direction as the current, my voltage drop is equal to negative IR. If I'm going through a resistor with the current in that direction, but I'm traveling in this direction, it's going to be positive IR. So for resistors, 2 directions are important. The direction that you're going through the resistor as you calculate the loop rule, and the direction of the current. For batteries, only the direction that you're traveling through the circuit is important. If I'm going in this direction, or if I'm going like that, this first one, plus or minus IR, or plus or minus voltage of the battery, is plus, because I'm going from low potential to high potential. So my electrons are actually gaining energy as they go across that battery. Here, they lose energy, so I have a negative V. And so you want to keep that in mind as you're writing your loop rule, or as you're looking at the equations that are either correct or incorrect. So let's just write a loop rule here. I'll do it for this loop right here. I'm going to start right here and go in this direction. Negative 3 minus 4 I2 plus 5 equals to 0. I chose that to write this loop rule because let's say that I want to know I2, then it's just really easy for me to find I2. It's a single step that I can find I2. And so I2 is equal to negative 5, negative 2 is equal to 1/2 an amp. And it comes out positive, so I know that I've chosen the direction of I2 correctly. All right? You likely will, have a problem that requires not a single step mathematically, but 2 steps, where you have to solve first for I2, and then say solve for, I don't know what, Yes, now you have to solve for I1. Let's say I wanted to know I1 in this case. The easiest way would be to first solve for I2 and then solve for I1. So if I wanted to know I1, I would write my loop rule again, starting at that point and going in that direction. Minus 2, coming around, plus 4I2, plus 3, minus 1I1 is equal to 0. And so if I wanted to know I1, I would first solve for I2. And so this is going to be minus 2, plus 2, plus 3, minus I1 equals to 0. So I1 equals 3 amps. So you might have a system of equations like that, but you will not have a system of equations where you have two unknowns and two equations, where you have to substitute one equation into another. Okay? Multi-loop circuits. 3 or 4 questions where you have to find the correct equation. You might have one where you just have to apply the loop rule at a certain junction. We've done some like that as well. Okay? What else? What's bothering you?
Can we just do refraction?
Refraction, yeah. Nothing too tricky on refraction. But again, if you don't know how to do it, it's everything's tricky, right? If you're uncertain about it. But you'll see two media first, likely. You'll have light traveling from one medium to another. I might give you a figure, or I might just describe it in words. Light travels from one medium with an index of refraction of, say, n equal 1.5 to another medium with an index of refraction of 1.8, say. With an incident angle of, say, 30 degrees, what is the refracted angle? And the refracted angle will be the angle that the ray in the new medium, what it travels at, as measured to the normal. So first of all, it's useful for you to know, does it bend towards or away from the normal? In this case, it does what? Bends toward or away from the normal? Towards. Very good, right? Because it enters that medium and it slows down. If I imagine my fronts, it slows down right here and this spins around, and so it's going to bend in this direction. And so theta 2, I know right off, is less than 30 degrees. It sure better be less than 30 degrees. You might only have one option that's less than 30 degrees, in which case you're done. But if you need to calculate it, we'll call this N1, this N2. You use the law of refraction. N1 sine theta 1 equals N2 sine theta 2. And then you solve for theta 2. So N1 is 1.5 sine of 30 divided by N2 is 1.8. And then you have to take the inverse sine of that. Okay? By the way, if I'm doing total internal reflection, the only difference is this angle is 90 degrees. That's how I determine my critical angle. And you'll likely have a question like that where you have to find the critical angle. Remember, if you're trying to calculate your critical angle and you get an error on your calculator, you might want to go back because it might be a scenario where you don't get total internal reflection. Like, for example, this scenario, I would not get total internal reflection because I'm moving from a low to high index, and this ray is never going to bend back up towards the medium into which it's entering. All right, that's probably not, you were probably asking about the ranking though, and let's do one of those two. Those are a little trickier in my opinion. So let's look at those where you'll have 3 media, N1, N2, and N3. And I want you to be able to rank. I'll give you some rays like this as they move through the different media. And I want you to rank either the speeds or the indices of refraction. The speeds that light travels through those media or the indices of refraction from lowest to highest or highest to lowest. I'm not sure what it'll be, but it'll say in the problem, of course. you want to take these piece by piece. And so is N1 bigger or smaller than N2? Well, imagine my wave fronts. What does it do here when it reaches N2? Does it speed up or slow down? It slows down. And since it slows down, N1 is smaller than N2. And then I can do the same for N2 to N3. Does it speed up or slow down? It speeds up, right? So that means that N2 is bigger than N3. And then I want to ask myself the question, looking at N1 to N3, I'm just going to draw it as a separate figure. N1, N3. That ray looks like this. I'm just drawing this portion and this portion, just getting rid of that N2 altogether. And then do the same thing. Speed up or slow down? It speeds up, right? So that means that N1 is what? Bigger than N3, right? See, these confuse me too, but they're useful. And ranking problems are good for you. Yeah.
Something speeds up from one to the other. If it goes faster, it's a smaller thing. Like,
Right. Because N, let's write it like this. V is equal to C divided by N. So if N goes up, V goes down. Or we wrote it, I think on your equation sheet it's N is equal to C divided by V. Okay, and now we would rank these. So N1 is bigger than N3, and it's less than N2. So N2 looks like our biggest one, followed by N1, followed by N3. And then the speeds are going to be exactly the opposite. So V3 is the biggest, followed by V1, followed by V2. You will have a ranking problem like that, where you have to rank either the speeds or the indices of refraction based on the figure. You absolutely will have that problem. Okay? You're going to have 3 or 4 multi-loop circuit problems. You're going to have this. You're going to have calculating the refracted angle of the light. That's a third of the test right there. What's the other thing? No big surprises. Although the questions will be different from what you've seen on other texts. They're always a little bit different. Look at your open stacks too. I'll pull questions from those, but they're they're similar to these two. They're all good test questions. Is that okay, Courtney? Yeah, those are good questions. Okay, let me pull up. What are these topics here? Stand out there to you? You want to just look at some old tests and see, or just sort of peruse some and see if anything stands out to you. Usually you're looking at exam 3 for this. Y'all have 16, right, in your book? Let's look at this 14. Sorry, it has to think for a minute. We're looking to get a new dog. Yeah. Huh? I don't know. We might actually purchase a dog. I feel funny about that because I know there are hundreds of dogs in the shelters, and I know that they all need homes. But I've always wanted to have a standard poodle, and so we might get a standard poodle. A big one, yes. But I don't know. We're going to look at the shelters and see. Ugh, come on. All right. So you'll have some capacitor stuff like this, something very similar to this where I give you a description and ask you to pick out what is the figure that describes it. Oh, that was it for that one. Sorry, folks. Something else I can tell you about? We're getting a dog. We're getting wait. What? A new car? No, we're not getting a car. We did, yeah. There's still glass rattling around. With cars, we think that cars need to have character. That's what we talk about. So we want our car to have lots of character. But a missing window, that's like a little bit too much character. But I told my wife we could just put cardboard and duct tape on. That works just fine. Like people do that all the time. She didn't go for it.
Do you name your cars?
Not yet. It doesn't have quite enough character. I'm sorry, folks. Do you name your cars, Marissa? No. We actually have Dr. Lowe's van. We bought it. It was a lease that he had it. Did you know this? Yeah. He's like the nicest guy, isn't he? I like him too. And he took good care of his vehicle. What? What did he say? Oh, okay. Here we go. Okay, again, capacitor stuff, multi-loop stuff. You might see one like this where you have extra junctions, or you have to apply the junction rule, but it works the same way. Incoming current equals outgoing current. You're going to have to calculate something, the charge, voltage, or current on a capacitor at a particular time. Know how to use those equations. They're provided for you. Just know how to use them. Basic stuff about magnetic fields here. Direction of the magnetic field, it runs from north to south. Here's force on the electron. That's just that F equals QVB. Y'all stop me if there's something you want to work through. Here's this one. You have to use your right-hand rule to figure out the force. Yeah. So the first thing you want to do is find the magnetic field. Two applications, right? First, the wire. The current is going in this direction. So into the page on the bottom, out of the page on the top. So my magnetic field is out of the page. And then I have V going down. Magnetic field is towards you. And so the force is to the left. And it is a positive particle, so the force will be to the left. Yeah. Yeah, sure. Hold up, is that what you said? Did I do that right? Yeah, I think so. Yeah, to the left. Is that good? If it was a negative, it would go to the right, yeah. Watch that. Like if you see an electron, or if I say that it's a negative particle, and that could happen, okay, so read very carefully as you're going through. Everything, read it. But if it's an electron or a negative particle, you take the opposite. Draw a big circle or something, because you'll probably go through the problem. By the time you get to the end, you'll forget that it's a negative particle. Can y'all do that for me? If it's a negative particle, just take the opposite. Right, yeah, if it was negative, it's to the right. It's a particle thing. Just take the opposite of what you can. Okay? What are you going to do if it's negative? Right. Yeah, so first you want to figure out the magnetic field. This particle enters a magnetic field. The current here is to the right, into the page, out of the page. So really I'm just dealing with this scenario. I have a velocity vector that is down and a magnetic field vector that's out of the page. And so what is the force on that? Well, V is down, V is out of the page, so that's to the left. So my force is to the left. Isn't that right? I did that correct, right? Yeah, that's right. Now let's see, I think there's... Oh, make sure you know how to do the mass spectrometer with this, where you find the mass to charge ratio. I haven't forgotten your question. We're getting to it. Electromagnetic spectrum, I didn't mention that, but yeah, electromagnetic spectrum, wavelength, frequency, and energy. Make sure you can rank those in that order. Okay, here's one with the angle of reflection. With these, you just need to know that the incident is equal to the reflected angle. So for example, when this reflects off, this angle is 30 degrees. And then you need to know a little bit of right angle trigonometry, or just you need to know your geometry for right angles, triangles. If that angle is 30 degrees, that means this angle is 90 minus 30, or 60 degrees. And if that angle is 60 degrees, that means that this angle is 180 minus the sum of these, or just 90 minus 60, which is 30 degrees. And then that means that this angle right here is 60 degrees, which means that this angle is 60 degrees, and that's the answer, 60 degrees. All right. Who asked that? Was that you, Rebecca? Yeah. You will have a problem like this, but it'll be a different situation. Either I'll change this angle, or probably change both of those angles. But it'll look very, very similar. All right? Okay, anything else here? The critical angle here, number 21. Remember, just law of reflection. N1 sine theta 1 equals N2 sine of 90. And so this just goes away. It's equal to 1. And then this theta 1 becomes our critical angle. There's an equation for the critical angle on your equation sheet where it does theta c is the inverse sine of N2 over N1. But I find that a little difficult because you'll get N1 and N2 mixed up. But if we just stick to what we know already, then we'll keep our N1 and N2, I think, straight. So here I'm going from benzene to air. Benzene to air, so benzene is 1.8. Is 1.8 for N1. 1.8 sine of theta c is equal to 1, and then I solve that for theta c. And here I'm moving from a high index to a low index. So I know that I will get total internal reflection. There is a critical angle for this, but if I was moving from low index to high index, then it would not. You'd get an error anyway because of the error. But if you get an error, we'll just switch the numbers, because that might mean that you just go back and read the problem and make sure that you're going from high to low. If you forget, is it high to low or low to high? Think about fiber optics, right? Glass surrounded by air, what is that? That's a high index surrounded by a low index. It's not actually glass surrounded by air, but it could be if you wanted it to be. All right. What else, people? You want to go and take the exam right now? No. Yeah, Abby? Yeah. Yeah, sure. So, let's see. Is there one here? Oh, yeah, there's one. Yeah, so this would sort of fall into my right-hand rule category of that spreadsheet that I showed you. So, a couple things you need to do here. First, ask yourself, what is the direction of the magnetic field? North to south, right? So my magnetic field is in that direction. And then just take one side of the coil. I'll take the left-hand side. I have a magnetic field that's in that direction, and I have a current that is into the page. That is this side, the left-hand side. So my current is into the page. My magnetic field is to the right. And so my force on that left-hand side is going to be downward. My force over here is down. And because I know that the current on the other side is just the opposite direction, but otherwise the same, the force on that side is going to be upward. And so that's going to cause it to move, what is that? Counterclockwise. Okay? And you could have one like that or something similar. What direction this is. Okay? Also, with regards to that, remember with the electric motors that you have to change the direction of the current every half turn. Otherwise, it flip-flops. Y'all know how to do this, number 17? Yeah. Remember, you have an equation in your equation sheet, but remember that our magnetic force is equal to our centripetal force, mv squared over r, and that's how I get the cyclotron equation, which is that, what is it? That goes away. It's mv over qb. mv over qb. That's what you have, I think, in your equation sheet. That's the cyclotron equation. It allows you to find the radius of the path that the charged particle takes when it's in a magnetic field. But we can use it in this case to find our mass to charge ratio. M over Q is equal to RB over V. And so my radius is 0.5. My magnetic field is 8.5. 8 over V, which is 4. So it's 1. The ratio of mass to charge is 1. That means that the answer is lithium, because my mass to charge ratio 1 to 1, whereas this is 2 to 1, 4 to 1, or 16 to 1. You'll probably have one like that, and then also some conceptual questions about the mass spectrometer, which are really just applications of the right angle. Anything else, people? No? All right. Well, that's all then. I'll see you on Wednesday. I'll be around tomorrow, so if you need anything, please do come see me. Wednesday, this room, and I'll give you the seating charts from the whole room.